This video is going to be for both statics and dynamics, since they're pretty similar and this problem contains both. You can make your note cards for each. The difference is that in statics, we know that we're going to add all the forces together from a free body diagram and set them equal to 0. And in dynamics, we're going to set all the forces together and we're going to set them equal to ma because it causes an acceleration. The one mildly confusing thing is that you're going to use this one for statics and when v is constant. Because when v is constant, then we have no acceleration. If we have no acceleration, then sigma f equals 0. So in this problem, it has a constant v, but we use the sigma f equals 0, not the sigma f equals ma for the first part. So let's get started. On both types of problems, you always have to do a free body diagram. So you need to really hit that hard on your note card for both of them. And on a free body diagram, you might want to put a list of ones to do. You always start with gravity. Gravity always goes down, and for part A I'm supposed to draw all my forces on there, so I put gravity going down. The next one to check for is probably normal force. You only have normal force when you have a surface. On this one I have a surface. Normal force always goes directly out of the surface, so I put normal force directly out of my surface, right up like that. The next one to look for is frictional force, and they have to give you a mu to find this. If they say that it's frictionless, we don't put this one on. Frictional force always goes opposite the motion. Since my motion is going down the incline, my friction has to go up the incline. And the last one on this problem is tension. And if you have a rope in a problem, you have to have tension. And tension will always pull, not push. So since this rope here is attached on this side, I have to have the force tension all going up the hill. And that's all of my forces that I have on M1. And I'm going to use those in part B. In part B, it starts talking about the forces, and it gives me some variables to put it in terms of, so I need to make sure I always use those. But it's asking me about friction. So I put the basic equation for friction first. I write F of F equals mu F of N. And that's, what friction is. But I want to put it in terms that they give me. And they told me that the friction on block 1 is F. So I use a little f there. Mu is what I'm going to solve for, so I can put in whatever terms I want. I have to know what the normal force is. Remember, to find normal force, it's a matching force, so I need to find on my free body diagram what goes exactly opposite it. And in this case, it's a part of gravity. Not all of gravity. Gravity is going to go straight down. I know gravity is mg, because that's my formula. And I'm going to split gravity into a component that's down the incline and into the incline. One reason is because I want to find normal force here. I need to find this side, which I call FGY. Eventually, I'm going to find FGX also. And this angle up here is always the same as the angle at the bottom down there, theta. You could do a little right triangle if you need to figure that out. But anyway, I need to find this, and so that's the hypotenuse, mg, times the cosine of the angle because it's the adjacent side. Then I put that in for my normal force because they cancel out, so I put mg cosine theta in there, and I can solve for mu. My mu becomes, not just mg, m1g. This becomes f divided by m1g cosine theta. And I want to go ahead and make sure that I'm just using things up here that they told me to put it in terms of. If I had left that m in there accidentally, I would have noticed that m isn't there. I would have put m1 in, so I would have gotten that right. And so they're taking just one little force there, not the whole sum of the forces, to try to give you some easier points, I think. And so look for B to be a little bit easier on these. Don't necessarily go for the big full-blown thing, which we're going to do on C. On C, since it's asking us to find the value of the suspended mass m, we can use the whole object as one big object. The reason we want to do that is because then we can ignore the tensions in there and just look at the forces on all 3 blocks, and we don't have to get all complicated with 2 different tensions, and we have a lot more forces. Because it's going at a constant velocity, we can use the sigma f equals 0 problem. And when we do these, a lot of times we set all the forces going to the right equal to all the forces going to the left. I mean, technically we should say the ones going to the right are all positive, the ones going to the left are all negative, and then I can move them to the other side. But it's easier just to start with setting them equal. And so I talk about all the ones going to the left first. To the left, I have this FGX, because notice it's going to the left. This is going to be m1g sine theta. So to the left, I have m1g sine theta. I also have the exact same thing from m2. I'm not even going to draw it because it's nothing different in the picture. It's m2g sine theta. And going to the right, I have big mg, because that makes the whole thing move this way. I have the friction from this one, because it's going up. That's little f. And then I have the friction from block 2, which is 2f. This is the x side, like I didn't say, but this is a 2-dimensional, but the y side always cancels, and they gave me the friction, so I don't even need to write down, the that the normal equals the friction. So I can just go straight to the x. It's a hard problem because it has lots of variables, but they tried to make it easier for you some little ways, and one of them was that we didn't have to do the y, we just had to do the x. And so then I want to solve for m. I got a lot of variables, but don't let that confuse you. I just keep powering through. I'm going to take these two f's and put them on the other side. So I have m1g sine theta plus m2g sine theta minus 3f equals big mg. Divide everything by g. And I get that m equals, this becomes m2 sine theta plus, oh, that's a 1. m1 sine theta plus m2 sine theta minus 3f over g. Notice I canceled the g's in those two, but I couldn't in that one because it didn't have a g. And that is my answer for C. For D, and I'm going to have to move it up a bit, I have now cut the string, and so this is the sigma f equals ma part, because it's going to actually accelerate down the incline. And since they're just telling me to deal with the first mass, it's a little bit easier because I don't have to do the m2 stuff, I don't have the 2f stuff. What I'm basically going to say in this, and again I can ignore the y's because they already give me the f, I say sigma f equals ma, and it's m1a. And all my forces, all I have left is m1g sine theta and f. Everything else goes away because it was for the other block. That has to equal m1 times a. So pretty simply I can solve for a. A equals g sine theta minus f over m1. And I'm finished with my problem. When you're writing up your cards for these, I would suggest making a list of the forces you could have, and maybe even putting the formulas for those forces on it. And you can use the card that's above it, but having a list of those on there can help you to know what to put on there. And put the directions for all of them so you know where to put them on there. There's a rule for the direction on almost everything, and so it's nice to put those on your statics and dynamics card. A lot about the free body diagram, X and Y components, that sort of thing. All right, that's it.